at another example illustrating this airy stress function approach. So now let us take a cantilever beam. So this is something which you have seen in your strength of materials courses. So there is a load P that is acting in this particular direction here. This is the x-axis, this is the y-axis here, and the length of this cantilever is L. So you are already familiar with your strength of materials formulae such as the deflection, right? That is PL cube by 3I, all those kind of formulae. But now, see, those formulae were derived under certain assumptions, right? And here, now we are trying to see whether we can find a more accurate solution than that one, right? So as I said, that there are lots of assumptions that are made. So for example, we are ignoring the effects of the shear stresses and so on, but now we will try to find an exact solution to this particular problem here within the context of linear elasticity. So we will look for an airy stress function that satisfies all the appropriate boundary conditions here. So here the one thing to remember is that when I write this load P, this is not actually a point load. Okay, so this, whenever I draw this load P, is actually it is a resultant due to the traction distribution that is applied on the right edge here. So this, although I may show it like a point load, but you should always remember, I mean, so this is applicable throughout the course, except in certain cases where I will point out that it's actually a point load. Okay, but generally speaking, even if I show something like a point load, it's actually the resultant due to the tractions that are being applied on this right edge. So basically, if I draw this right edge here, then there is some distribution of tractions here, like this shear tractions here, and then when you integrate all these shear tractions on this particular edge, then the resultant of that integration will be this P here. So here let us write the airy stress function as minus 2PL by T H cube times y cube plus 2P divided by T H cube times xy cube minus 3 by 2 times P times xy divided by T times h. So here this T is the thickness into the board. So T is the thickness in the z direction, right? And then this. So again, I mean the same thing here, that typically the way these airy stress functions are formed is that you first start with some set of polynomial functions that are biharmonic. Right? So basically you will see that y cube is biharmonic, then xy cube is biharmonic, then xy is biharmonic. Okay, and so you basically try out. So it's a process of trial and error. The way we are learning it here. As I said, there is a systematic approach, but we will not get into that at this stage. So here, at least for this particular example, we try out various biharmonic functions, and then what we do is that we will adjust these coefficients, right, so that the boundary conditions are met. Now, somebody has already done this job for us, and that's why I am just writing out the complete airy stress function directly. But suppose if I did not know the solution to a particular problem, then I would have to find these coefficients. I mean, or even the functions itself I will have to find. So I will start with some big set of biharmonic functions, and then keep on trying to adjust the coefficients to see if I can satisfy the boundary conditions. And it may happen that the set of biharmonic functions that I have started with is not sufficient, right? And so then in that case, I may have to add more and more functions to that particular set. So it's a little bit of trial and error process. And then, so using this trial and error process, we have now figured out what this airy stress function is. And now I want to find out whether this is the appropriate airy stress function for this particular problem here. Alright, so here, so we'll take that this particular end of the beam is fixed, and then the right end is subjected to some traction loading, which results in this load P. Fine. Now let us look at what are the stresses that are generated by this area stress function. So one is that your tau yy is equal to del square phi by del x square, that is equal to 0. So this is everywhere. Then second is that tau xy at y equal to plus minus h by 2 is equal to minus del square phi by del x del y. So this is at y equal to plus minus h by 2. So this is also equal to 0. Then the third thing is tau xx at x equal to L is equal to del square phi by del y square at x equal to L, and that is also equal to 0. So I am just evaluating the various quantities using the at various locations here. So this I am evaluating tau xy at y equal to plus minus h by 2. So that is on this particular edge and on this particular edge. Then tau xx at x equal to L. So that is on this particular edge, the normal stress. So that is equal to 0. Okay. So now let us look at whether the boundary conditions are satisfied. So here, as I said, that see on this particular edge. So in the last example we showed, right? So here your tau xx should be equal to 0, right? Because there is no normal traction that is being applied on this particular edge here, correct? And so that you can see that this tau xx at x equal to L, so this should be capital L here. So this at x equal to L, that tau xx is equal to 0. So that you can see this boundary condition is satisfied. Now there is a traction distribution here, tau xy. Okay, so this along this particular edge, the tau xy is not 0 because the integral of that tau xy is what is giving us this resultant load P. Then how about the top surface and the bottom surface? So here you can see that this surface is also traction free. This surface is also traction free. And then in the last class we saw that the appropriate tractions components on this one is that your tau xy should be equal to 0 and your tau yy should also be equal to 0, because those are the appropriate traction components on the top edge. And similarly on the bottom edge, the same way, that because this is traction free, you will get that tau xy 0 and tau yy 0 on this bottom edge also. So here you can see that tau yy is 0 everywhere. So I don't even need to bother. I mean, so it's not just that on the edge alone, but entire, I mean, throughout the structure. So this boundary condition is automatically met. So that is the first thing here. Then tau xy at y equal to plus minus h by 2, that is also 0. Correct? So that also, this condition is met on the top surface and the bottom surface. Right? So this surface is now taken care of. The boundary condition on that particular surface are satisfied. Similarly, this surface is also taken care of because that boundary condition is also satisfied. Then on this particular surface, we have verified that the normal tractions are 0. So that is this particular condition here. Right. Then now we need to verify. So in this particular case, see this, you can see that the coefficients are functions of P. Correct. So that is the resultant load. So actually, the way we find out that is that we take like a free body diagram of this one, right? And then the integral of the tractions integrated along this particular surface should be equal to P. So actually you don't need the free body diagram, just on this particular surface itself if you consider, that's also fine. So you will just the integral of the traction distribution along this should give you this P. So let us try to verify that. So if I write now integral of tau xy times t times dy from minus h by 2 to h by 2, right? So that is a traction in the y direction. So this is basically integral. Just write it. So this is integral of ty times t times dy from minus h by 2 to h by 2. And ty, that is the traction along the y direction, is nothing but tau x. And so that is this integral. And then you will see that this is equal to integral of minus del square p by del x del y times t times dy. And so that will come out to be p. So you can see that, so that is how actually the coefficients are found. Okay, so coefficients as functions of p are found from this particular condition here, that your traction distribution integrated over that particular surface should be equal to 0. Now, if you take this free body diagram, as I was saying, then now let us look at what is the moment now at any section. So this length here, suppose if this distance is x, then this length here is L minus x. Okay, so let us look at now what the moment is at a given section. So integral of tau xx times t times just 1 second, the moment, sorry about that, this I think is just the resultant force. I'm sorry about that, just 1 second. So this is okay, so first let us just find the force and then we will find the moment. Okay, so this is tau xx t dy minus h by 2 to h by 2. So this actually comes out to be 0 here. That is because the resultant load is acting in the y direction, right? And so if you draw this free body diagram, then the resultant force in this particular direction is going to be 0, because there is no resultant force that is acting in this particular direction, right? So and there is nothing, no tractions that are acting on the top and the bottom surface. So this integral comes out to be 0. So that is, if you actually plug in your tau xx into this, you will see that it is equal to 0. Now let us look at the moment. So this, if I find out the moment using that formula x cross t ds, right? So if you find that from minus h by 2 to h by 2 of tau xx times y times t times dy. Okay? So that will come out to be minus p times L minus x here. Right. So you can see that so if I take a point here, right, the moment due to the load p is p into L minus x, and so that is balanced exactly by the moment due to the tau xx that is acting on this particular section. So that finally, the block has to be, any subpart of this cantilever has to be in equilibrium, right? And so this moment is balanced completely by the moment due to the tau xx about this particular point here, and so that comes out exactly as minus p to L minus x. So this is just a verification that your solution is correct. So actually, I mean, as I said, that we don't need to use these conditions in order to find the constants. So the constants are found just by using the boundary conditions along the top and the bottom and the side surfaces. So, but once the constants are found, then this is sort of a verification that we indeed get the moments that are expected at a given section, or we indeed get the forces that are expected at a given section, and so on and so forth, right? Fine. Then, so let us now look at what the solution looks like. Okay. So now we will do a little bit of analysis on this particular solution here. Okay. So. Yes. So if I find now the expressions for these stresses, so I will get that tau xx minus P times L minus X times Y divided by I Z Z. Okay. So it will come out as this particular formula. So I Z Z is nothing but your moment of inertia. So this is T H cubed by 12. So this formula is exactly matching your strength of material solution, right? So now see, so we have not made the usual assumptions that you make in your strength of material solution. So this is based now on an exact solution, right, for the plane stress case. And what we have done is that we have found out what the Airy stress function is, and then we have found out what is the stress from that Airy stress function, and you will see that it exactly matches your strength of material solution, because P into L minus X is the moment which I just calculated here, right? So this is actually equal to minus of M times Y divided by I Z. So this M is equal to P times L minus X is the moment at any given section here. So you can see that the strength of materials formula, although that was derived based on using some assumptions, is a very good approximation to this particular solution. So, okay, but one thing you have to bear in mind is that only this particular aspect of the solution is matching. So not, I mean, the whole solution is not going to match. So for example, the displacement field will be a little bit different. So only the center line deflection from this solution will match your strength of material solution. So that we will see. So the solution here is going to be more complicated than your strength of material solution, but certain aspects of the strength of material solution will match this particular solution. Okay, so that is what we are seeing here. Then tau y is 0. So this is also an assumption that we make in the strength of material solution, right? That when we apply this load, we assume that there is no stress in the y direction. Then tau xy is equal to P times x squared by 4 minus y squared divided by 2 times I zz. And this formula is also matching with your VQ by I zz times P. Okay, so this is also in agreement with that particular formula, where this Q, if you recall, is the first moment, right, of this area. So suppose this is your neutral plane, and then you compute the V based, the Q based on that. The V is of course just the shear force, which is equal to P in this particular case. So Q is that first moment of this particular area at a given height. And so that turns out to be h square by 4 minus y square. So even this shear stress distribution also matches. So whatever comes out of the theory of elasticity also matches the strength of materials formula. Okay, so that's also, so you will see that in many cases. So even when at a later stage we will do torsion of circular cylinders, you will see that even there the strength of material solution is a very, very good approximation to the exact solution. Here, the only problem with this solution is that your tau xx plus tau yy is not of the form ax plus by plus c. So that means some of the compatibility relations are violated. Some of the compatibility relations, are violated. So that is fine. I know. So as we discussed, the plane stress is also an approximation, right? And so so this is also fine. So within the context of the plane stress approximation, this is an exact solution. But here we'll see that the out of plane compatibility relation. So the in plane compatibility relation is of course satisfied, because that is what we used to get the equation that del raised to 4 equal to 0. But the out of plane compatibility relation, some of them are going to be violated. we will study a beam theory, which is the Savena beam theory, where we will not even make the assumption of plane stress also. Okay, and in that case, that will be a fully three-dimensional solution, and then so that will be even more exact than this solution. Okay, so you can think of it as three levels of solution. So we are basically studying three levels of solution. One is your strength of material solution, where there are several kinematic assumptions that are being made. Then this solution is a plane stress solution, where you are making the assumption of plane stress, and that still violates some of the compatibility relations. And then towards the end of the semester, we will study a fully three-dimensional solution which doesn't make the assumption of plane stress also. And so that will be sort of the most exact solution that we are going to study in this particular course. And so we will see that this solution will also be a good approximation to that more exact solution that we will study towards the end of the semester. Fine. So we will continue from here. Now let us look at the displacement field. So as I said that not everything is going to match with your strength of material solution, and that you will see for the displacement field is fairly complicated here. Just one comment I would like to make here is that, see, this is where the Savena principle comes in. Okay, so here you can see that this tau xy has a parabolic distribution here, right? So let us draw this particular section here. So here this distribution of the shear is in this parabolic form, right? It is a maximum at the center, and it goes to 0 at the two ends. So for this whole solution to hold, your load P should be applied in this particular manner. It should be applied, so only when the tractions are applied in this parabolic distribution will this solution emerge. Correct? So, but in a practical situation, you may not apply the load in this particular fashion, right? In a practical situation, maybe you just put a nail into this and just hang a load by a thread. Correct? So that, I mean, what I'm trying to say is that in that particular case, what the Savena principle says is that in the vicinity of the load, where in the vicinity of the region where the load is applied, the stress distribution will be very different. Okay, so as I said that here the distribution is parabolic, but if I suppose hang a weight, right, by a thread, then in that case, in the vicinity of these two cases, the stress distribution will be very different. But if you go very far away, right, if you go somewhere near to the wall, then the stress distributions will almost be the same. So that is what that Savena principle that I discussed a couple of classes ago, that is what that says basically. So as I said, there is no really rigorous proof of this Savena principle, because how far do you go from the load, all those are tricky issues. But this is something that has been found experimentally to work quite well, and so we will just accept that. So that is one thing that I wanted to mention, because many of you may be confused about what the use of that Savena principle is. So this is the place where that Savena principle is used. That so basically we are saying that the exact solution is not completely useless. I mean, obviously, suppose if the stress distribution, if I hang a load by a thread, and if I actually find applied by a parabolic distribution, if the stress distributions are completely different, then this exact solution is of no use to me, right? Because I am applying the load in a different way. But what the Savena principle says is that actually that exact solution can be used, because except in this very narrow zone near to where the load is applied, far away you can apply. So more or less you will find that actually even if you don't apply the load exactly in the manner prescribed by the exact solution, the displacements, the stresses will match. I mean, experimentally, whatever observed will match with this exact solution. I mean, almost. I mean, not to a very close approximation. And so we we can use all these solutions even in a practical situation also. Fine. So now let us move on to the displacement field. So that part is a little bit tricky. So first, so the way it works is like this, that first you find the stress field, because the area stress function is given and the stresses can be directly expressed in terms of the area stress function, but the displacements cannot be found directly from the area stress function. So what you have to do is, now from this stress distribution you have to find out what is the strain distribution, then use the strain displacement relation and integrate that strain displacement relation in order to find the displacement field. So it's a very laborious process to do this, but in principle a single value displacement field will always exist. That is because we have ensured that the in-plane compatibility relations are satisfied, right? So that's how we derived the del raised to 4 phi equal to 0. So once we have ensured that the in-plane compatibility relation is satisfied, a single value displacement field will always exist in principle. So what I mean by in principle is that suppose the stress distribution is some horribly complicated function which you may not be able to integrate analytically, but conceptually that is not a problem. Okay, so in principle it will still yield a single value displacement. So we are not talking of difficulties in integration like in your 12th standard. We may not be able to integrate some complicated function. So that is not what we are talking about. In principle, a single value displacement field exists. So that is what is more important. So whereas if the compatibility relations are violated, then there is no displacement field. Basically, there is no single value displacement field which will satisfy all your governing equations. Okay, so now let us look at what the displacement field is corresponding to this stress distribution. Yes, so as I said, this process is a bit laborious. So let me just write this whole thing down. So epsilon xx is equal to del ux by del x, or let me indicate the components as so u and v. So these are the displacement components in the x and the y directions. So del u by del x, so this is equal to 1 by e times tau xx. So that is because the other tau yy is 0 and tau zz is also 0, because this is a plane stress situation. So this is equal to minus p times L minus x times y divided by e times I z. And epsilon yy is equal to del v by del y is equal to minus 1 by e times mu times tau xx. So this is p times mu times L minus x times y divided by e I z. And gamma xy is equal to del u by del y plus del v by del x is equal to p divided by 2e times I zz times x squared by 4 minus y squared. Okay, so these are the three equations A, B, and C. So this so basically what I have to do is now I have to integrate in some sense these relations, these three relations, in order to find u and v. And as I said, that since we have already ensured compatibility, we know that such a displacement field exists. So in this particular case, we are able to actually integrate these relations in order to find what u and v are. So I'll just indicate this whole procedure. So I'm not going to go through the details because as I said, it's a very complicated process. But let me just indicate how to do that. So from A, so let me just write. So from A, what you will get is that u is equal to minus p divided by e I z times L y x minus x square y divided by 2 plus g1 of y times p divided by e I z z. So this to x, this part will vanish, correct? So you have to add, so this is like an integration constant, right? Except that in this particular case, because these are partial differential equations, you have to have a function of y, okay? And then similarly, similar things will happen even for the other case also. So then v will be equal to p times v divided by e times I z times L y square divided by 2 minus xy square divided by 2 plus g2 of x times p divided by e times I z. So this is from b now. So from b. Okay. So same thing. I mean, what I have done is that I have integrated this particular equation, but now I have to add a function of x. Then now I need to determine this function of y and this function of x. So what I have to do is that now I have to use this equation c now. So I will substitute this particular these components into this particular equation, and then I need to find out what this g1 of y and g2 of x is. So that whole process is a little bit complicated, so I am not going to go into all the details of that. You can try this whole process yourself. So I am just going to give you the final expressions. Okay, so this is something that you can work out yourself. So finally, just give the final result. So one thing is that at least if I give you the final result, you should be able to verify whether all the three are satisfied or not. But in actually in finding these functions g1 of y and g2 of x, I need to give certain boundary conditions here. Okay, so this is the edge that we have not talked about so far. So let me just mention what are the boundary conditions that are being used there. The integration, so there will be some integration constants even within that g1 of y and g2 of x. So those are determined by as follows. So integration constants. So these integration constants are basically associated with rigid motion. Okay? And we have seen that there are three rigid modes in a planar problem, right? So that is your wx plus c. This is a rigid mode, and w will have only one independent component because this is a 2D problem, and c is a vector that will have two components. So those three rigid body modes need to be suppressed, right? And those are suppressed by prescribing appropriate boundary conditions at this left end here. So these integration constants associated with the rigid motion, rigid motion are found using let's say u is equal to v is equal to 0 at x equal to y equal to 0 and del v by del x equal to 0 at x equal to y equal to 0 at x equal to y equal to 0. So basically, this is the usual slope condition that we use for a cantilever beam, that we are saying that the slope of the vertical displacement evaluated at this particular point here. So that is equal to 0. So in reality, actually, the displacement should be 0 along the whole edge. But this solution will not satisfy that. So I keep repeating this, that the moment you have a finite number of terms in your area stress function, typically you will not be able to satisfy all the boundary conditions. So this is again another example. So the previous example also we were not able to satisfy all the boundary conditions. In the same way, even in this example also, you will not be able to satisfy this. Suppose if you give a boundary condition that the displacement should be 0, both u and v displacement should be 0 along this whole edge, you will see that this solution that I am going to now present for u and v will not satisfy it. So it satisfies it only at certain points. So that is this, at the center point, this displacement is 0 and this del v by del x is 0. But these three conditions are enough to suppress the rigid body motion in this case. So here basically you will get some non-zero displacement here at this, at other point, other than the center, you will get some non-zero displacement. But that is fine. As I said, that finally we are looking at some kind of an approximation. Again, if you wanted to meet this condition exactly, then again you have to go to the more exact approach where it would be an infinite series. And that, as I said, that you have to take a look at the book. The 6th chapter of the book discusses that. That approach is very, very complicated. And as I said, that we are not going to go into that particular approach in this particular course here. Okay, so let us now write the final expressions for the displacement field. So let us write that. So this is U is equal to minus P divided by E I Z Z times L x y minus x square y divided by 2 plus mu y cube divided by 6 plus 1 plus mu times x square y by 4, so this is x square y by 4 minus y cube by 3, and V is equal to P divided by E I Z Z times mu times L y square divided by 2 minus x y square divided by 2 plus L x square divided by 2 minus x cube divided by 6. So this is definitely much more complicated than what you have learned in your strength of material solution. So in your strength of material solution, we basically assume that the displacement field is a function only of x, right? So we basically neglect, so it is like this, that suppose if the mid fiber deflects in this particular way, then we assume that even the top fiber also deflects in the same way. So everything is just a function of x. There is no y involved when we write the displacement field in your strength of material solution. So that is an assumption that we are making. But now you will see that using the more exact theory of elasticity approach, you will see that now the displacement field is a function of both x and y. So that is what I said that in the beginning, that some aspects of the solution, like the stress field, matches with your strength of material solution, but some other aspects, such as the displacement field, are not going to match perfectly, but we will see in what aspect they match now. And so it's really very, very interesting to see that actually your strength of material solution is still very close to this exact solution. So suppose now if I find V at y equals to 0, so if I find now the vertical displacement along the center line, so this is now the center line, and now you are trying to find out what is the deflection of this center line here. So that is V evaluated at y equal to 0. So this will give me P divided by 2 times E times I z z times L x square minus x cube divided by 3. And this is exactly the strength of material solution. Right? So this is exactly the strength of material solution. And so it is really, really interesting that that the more exact approach, using the theory of elasticity, and they are solving a bunch of partial differential equations subject to some boundary condition, finally the solution that you get is very, very close to the strength of material solution. So basically, even if you go to the top fiber, right, the effect of this y is fairly minimal. I mean, it is there, of course. So the top fiber is not going to deflect in exactly the same way as the mid fiber, but that deviation will be very small from the center line deflection. So that is why that strength of material solution works, and so that is why it gives almost, the correct stress distribution and so on and so forth. So the effect of this y is fairly minimal. That is what basically it is saying here. Actually we will see that even when we do the more exact solution than this towards the end of the semester, we will see that there in that more exact solution, we will relax even the plane stress assumption, right? So we will not meet the plane stress assumption, and then we will see that even this solution is a very good approximation to that one, provided the thickness is small. So that means now I am talking of the thickness into the board, right? So let us take this cross section. So suppose if the thickness of this beam is small, then this plane stress solution is a very good approximation to the exact solution in that particular case, and this plane stress solution will start deviating from the exact solution provided this thickness of the beam that is into the board starts getting large. Okay, in that particular case, this solution will start deviating. So that is going to be the final level. So that means the 3D. So that is going to be the 3D exact solution. This you can call as the 2D exact solution in some sense here. Right, now one last aspect of this one here is the boundary condition. Okay, so here we have taken this as the boundary condition, right? And this is the boundary condition that we typically use in this strength of material solution. But here, because we have more choice, because u is a function of x and y, and v is also a function of x and y. So another possible boundary condition here is that you can also use del u by del y at this particular thing. So that is like this here. So this here you can also use del u by del y at x equal to y equal to 0 is equal to 0. So this is also another boundary condition that can be used here. See, these things actually theory cannot decide whether to use this particular boundary condition or to use this particular boundary condition, because so what I am trying to say is that will depend on your actual experimental setup. So which one is more appropriate to use. So sometimes I think I have seen books saying that maybe even this is closer to the experimental data than this one. So, but as I said, that is something that theory cannot resolve. So that is something that how your beam is fixed into the wall, right? So those are practical details that have to be brought in to determine which particular boundary condition to use. So this, of course, this boundary condition you use in place of this boundary condition. So you cannot use both of them because, as I said, there are only 3 constants, right? In the Wx plus C, there are only 3 constants that need to be determined. So if you use this particular boundary condition, then it may give a slightly different solution than this one. But as I said, that some books say that this boundary condition may give a better approximation to the actual experimental data than that one. But as I said, that these are issues which we will not get into. So this is basically, suppose u is this particular displacement, right? And so we are saying that here the slope of that particular horizontal displacement is 0 with respect to y. Okay, so this boundary condition is not very intuitive. This one is more intuitive because we are used to seeing this particular boundary condition in our strength of materials solutions. But see, the point I am trying to make it is that different types of boundary conditions are possible when we are talking about these particular things here. Okay, and then the last point is that once you find these stresses, then after that you can find out what are the principal stresses and so on, and then you can substitute that into some failure theory to find out whether the yield criterion is met, whether it goes into some plastic yielding, so all those kind of things. So once you have this exact solution, then of course you can proceed to those different types of things. So all these solutions, I will emphasize, are valid only when your deformations are small. So that means this basically the displacement and the displacement gradients are small. So suppose now you take that it's a really large load, and now the cantilever is deflecting by a very large amount. Then if your deflection is very large, then this kind of analysis you cannot do using this linear theory that we have discussed here. You need to go to the non-linear theory of elasticity in order to discuss this. But of course, that is outside the scope of this particular class here. But I'm just indicating that so you have to apply all. So these solutions are valid only within a particular range of validity, and that range of validity is if your displacement, both your displacement should also be small. The displacement should be small in comparison to the dimensions of the structure, and the displacement gradients should be small in comparison to 1 in terms of the magnitude. So this is something which we have to bear in mind while using this particular